All right. So the capacitor will resist in its own way by basically by charging, okay, and the inductor it will resist the motion by playing the opposite as the battery and by always opposing the change that is occurring in your signal. And so now we said is that what we said is that let's see what happens when we put two components in series with a AC battery, okay? And what I was saying is that we have a problem in dealing with this issue analytically, simply by just simply adding the two sine waves, because these two sine waves, they have different phases. And one general way, not only for electricity mechanism in general, if you want to solve the problem of two sine waves and the addition of two sine waves with different phases, we use the phasor diagram. So what's the phasor diagram? The sine waves are represented as vectors, as you can see here. Okay, delta V is equal to delta V max sine of omega t, right? So basically, delta V max is going to be the amplitude, and omega t plus phi is going to be the angle. Okay, as I was saying, omega t is the angle, the radian per second. You multiply by the time second, so that gives you omega as the radian. So with time, this thing will rotate with a constant radius equal to the maximum value. Okay. Now, how do we continue? So what happened? So I'm going to have delta V R, let's say at t equal to 0 to simplify. Since this phasor diagram is valid at any time, the easiest way is to put t equal to 0. Okay. So the addition of sine waves is treated as addition as vectors. Yeah. In other words, delta VR is going to give me 0 phase difference between the current I and delta VR. So basically, if I max, that if my generator equal to I max, then delta VR at equal to 0 will give me the same phase difference, which is basically the angle is equal to 0 because the phase is equal to 0. Okay. Now, delta VC will give me a phase equal to minus pi over 2. Now you can tell me, oh, but we saw that this was pi plus pi over 2. Let's go back here to the capacitor. What did we say? We said that the phase difference between the current and the voltage is equal to plus pi over 2. Why I put it in this form? Because in this problem here, I have as a given, I've given you the voltage difference, delta V, but I could have given you the current. Okay, so if I have given you the voltage difference, then the current is equal to the voltage plus pi over 2. But how about if I've given you the current? The current phi I, if phi I equal to 0, then phi V is going to be equal to minus pi over 2. Okay, so it really depends what's given. Okay, and remembering in this way will really, you just don't care what's given. You just put, if I've given you I with phi equal to 0, then you say that phi V equal to minus pi. If I've given you V with phi V equal to 0, then phi equal to plus pi. Okay, so delta VC was going to give me minus pi over 2. You may wonder, why did I given you here IT equal to I max sine of omega t, not delta V max sine of omega t? Because in these series, in this putting resistor and capacitor in series, what I have in common between the three of them is the current. The current is exactly the same, and the voltage is not the same. So here, I've given you the current, I'm asking you the voltage around the battery. Okay? So, what's the voltage of the battery? Now it's treated as vectors, so this is delta VC, that's delta VR. I'm going to add them as vectors. This is my delta VB, well, which is equal to delta VR plus delta VC. And now I can use Pythagoras. That is delta VB square equal to delta VR square plus delta VC square. And I'm going to replace delta VC square as Z square I max square plus R delta VR R square I max square. And consequently, I'm going to put delta VB equal to I max square root of R square plus delta C square, which is basically R. Okay, and now the effective impedance of my circuit is going to be ZRC equal to the square root of R squared plus ZC squared. Now, what's the phase between the voltage around the battery and the current around the battery? The voltage tangent of phi is equal to delta VC, which is this guy here, divided by delta VR. And so delta VC is equal to ZC Imax, delta VR R Imax, Imax and Imax go away, and I'm left with ZC divided by R, or 1 over RC omega. Okay? So this is the usage of the phasor diagram. First, we put them as vectors, and then we use trigonometry or Pythagoras to go from to calculate the maximum value of around the battery and the phase around the battery. So this phase phi is let me see if so basically what I'm going to say is that I'm going to write it down here. So in general, I'm going to have delta V of the battery equal delta V of the battery max sine of omega t plus phi. This is the general form, where delta VB max is basically equal to R squared plus ZC squared, okay? And the phi is basically, the phi is cotangent minus 1 or arctangent 1 over RC omega, okay? In this case, I have calculated the potential difference around my battery, given the current around my battery. Okay, now let's get things a little bit more complicated. Or before I go, let me discuss a little bit what happened here, okay? So if I have, Z is my reactance, okay? Now you can see in my Z, there's not only the values of the resistance and the capacitance, but also there's the value of omega, and omega is going to play an important role. How so? When omega tends to 0, omega tends to 0, this means that I am roughly a DC circuit. If I am a DC circuit, this means that 1 over, what I expect is that my current will be equal to 0, right? Because it's DC, my capacitor is fully charged, I have no current. Let's put it in this form here. Use this ZRC. If omega tends to 0, 1 over 0 is tends to infinity. Consequently, my Z will tend to infinity. And if I write delta V is equal to Zi, then my I will tend to 0. Okay? If I write here delta V equal to Z multiplied by I, okay? Or in other words, I equal delta V divided by capital Z. Possible? So if I'm using, if in the case here, as omega tends to 0, so omega goes to 0. Okay, then omega tends to 0. 1 over omega tends to infinity. This means Z tends to infinity. And if Z tends to infinity, this means that my I tends to 0 because delta V divided by Z. Okay. Now, what happened when omega tends to infinity? When omega tends to infinity, 1 over omega tends to 0. So my Z is equal to R. So my Z is equal to R. Basically, as if I don't have a capacitor. Okay? If I don't have a capacitor, this means that my I is equal to delta V divided by R. Okay? So when omega is very small, my capacitor is fully charged and my current is equal to 0. When omega is very high, this means that my capacitor does not have the time to charge or discharge, okay? And basically as if I have no capacitor and I only have a resistor in my circuit. Okay? Okay, let's continue with putting now an RLC circuit in series and see what happened in this case. Given Once again, look what's given. What's given is basically the current I. Once again, the reason why I'm giving you current I is because it is something which is common to all the three components. What's not common to the three components is the potential difference. So the issue is the following. I've given you I, and I want delta V around my AC power supply, my battery, my AC battery, okay? So the question is, what's delta V of the battery? What you can say is that, okay, delta V of the battery is equal to delta VR plus delta VL plus delta VC. Delta VR is going to give me 0 phase difference, okay? Delta VL is going to give me plus pi over 2 phase difference, and delta VC giving me minus pi over 2 phase difference. So immediately now what I'm going to go, I'm going to go and to the phasor diagram, okay, to solve this issue. So delta VR, I plot at t equal to 0 so that I don't have the time, and any result I'm gonna get is valid for at any time. So the delta VR gives me 0 phase, so this is my delta VR. Delta VC is minus pi over 2 phase difference, so my delta VC is downward. Delta VL is plus pi over 2 phase difference, so that's going to be in the plus y direction. That's plus pi over 2, that's minus pi over 2. So, but this is going to be is going to make my work easier. Why? Because delta VL and delta VC, they have exactly the same support. Okay, so they are on the y-axis. One is on the plus y, and the other one is minus y at all times, of course. Okay, at all times. All right. So what I can simply say is I can define delta VLC as delta VL minus delta VC. Okay. So as you can see here, we have delta VLC is delta VL minus delta VC, and this is what's shown in this black arrow here. Okay. Now I only have now two vectors, which are delta VLC and delta VR. Okay. And now I'm going to use Pythagoras. Delta V around the battery equal delta VLC squared plus delta VR squared, as it's shown here. And delta V R squared is equal to R Imax squared. Delta VL squared is equal to ZL Imax. Delta VC is equal to ZC Imax. I replace all of these. I now have delta V of the battery is equal to this Z effective, to this impedance, multiplied by Imax, because each of these terms have an Imax squared. It gets out of the square root, get me an Imax, and I'm left with ZF is equal to R squared plus ZL minus ZC squared. Now, for the phase, this is phi, tangent of phi equal to delta VLC divided by delta VR. What's delta VLC? Is equal to delta VL minus delta VC divided by R. Delta, once again, delta VL is equal to ZL Imax, delta VC equal to ZC Imax, delta VR is equal to R Imax. Consequently, tangent of phi is now simply ZL minus ZC divided by R. And in this case, I calculated delta VB max, which is equal to ZF Imax, and did the phase phi, which is equal to R tangent ZL minus ZC divided by R. And so I have my potential difference around my battery. Okay? So now this is, if phi is positive, then it's more inductive, then capacitive, etc. This is not important. Now, but the important point is the following. If we take Imax now, if we want to discuss, as we were discussing for as function of the frequency here. Okay, what happened when omega tends to 0 or when omega tends to 0? Okay. So let's see. When omega tends to 0, L omega tends to 0. 1 over omega C tends to infinity. Delta VB divided by infinity will tend to 0. Okay? I'm going to write it down. So what we have here, when omega tends to 0, we have L omega tends to 0. And 1 over omega C will tend to infinity. Consequently, my Z my Z will tend to infinity. If my Z tends to infinity, this means that my I max will tend to 0, since my I max equal to delta VB divided by Z. So this is why you have this region here, okay, where for low frequencies, my I is about 0. Okay, now let's see what happened at high frequencies. Okay, when omega tends to infinity. Omega tends to infinity, L omega will also tends to infinity. And 1 over omega C will tends to 0. So this means that my Z will also tends to infinity. If Z tends to infinity, also this means that my I max will tend to infinity, to 0. Okay. So once again, let's take a look. When omega tends to infinity, then my I max will tend to 0, which is basically here. But in between these two, I'm going to have a value for which my I max is maximum. For maximum, for I max is maximum, this means that my Z must be minimum. And the only place where I can reach Z is minimum is when my L omega is equal to 1 over omega C. Otherwise, since it's squared, if L omega is either smaller or greater than omega C, it will contribute because it's L omega minus 1 over omega C squared. And it will be, and my Z will be greater. Okay? So the only time, the time where I have, or the value for which I'm going to have I max to be maximum is my Z must be minimum. And this Z is minimum is when omega is equal to 1 over omega C, and consequently my omega 0 square is equal to 1 over LC, or my F0 is 1 over 2 pi square root of LC. This is what we call a resonance frequency. So at this resonance frequency, my current is maximum, and basically I'm filtering out, okay, all the frequencies which are below or above this F0. Okay, I hope this issue is clear, and I hope this discussion was clear. Okay, so this is basically, that's the end of now. Of course, there are many applications. What you call, for example, here you can see this is the average power, which was dissipated. The instantaneous power dissipated, P of T is equal to IT squared multiplied by R. This is the power dissipated. This is the power lost. Remember that the capacitor store electrical energy, the inductor store magnetic energy. Okay, so during this AC signal, the capacitor and the inductor are always storing and releasing energies. Okay, the only component which is actually dissipating, losing energy, is the resistor. So consequently, the power P of T is equal to I squared multiplied by R. The average power is the average over time. So it's the P integral over P of T multiplied by dt. And if I replace this by the values, I have sine square of omega t. Sine square of omega t, the average value of it is 1/2. And so I have I max square divided by 2R. And this is where the RMS definition comes from. We're going to define RMS as equal to I max divided by square root of 2, such that the average power dissipated is now I square RMS divided by multiplied by R. So this definition of the RMS can also be related to delta V. So I'm going to have delta V RMS is equal to delta V max divided by the square root of 2. Okay, so this is now the usage of this RMS is basically if you want to compare AC to DC signals, or for household, we have 220 volt, we say that AC, but what we denote by 220 volt is the RMS value and not the peak value. So the peak value is 210 volt and not 220. 220 volt is the RMS value. Okay, you can see that when L omega at the resonance frequency, okay, if you recall, what was my tangent of phi? Tangent of phi, the phase, okay, is delta VL minus delta VC. But at the resonance frequency, delta VL is exactly equal to delta VC, and consequently, my tangent of phi is equal to 0. Okay, and so I have a zero phase difference between the voltage and the current of the power supply, of the AC power supply. This is the quality factor, and this I trust that you guys can do it at home. Okay, and I consider this chapter is basically done. And now we're gonna open for questions.